Welcome to the deep dive. Today we're digging into something really critical with some fascinating science behind it. ANTECY's new way of pulling CO2 right out of the air. We've got their detailed report here, laying out their solid sorbent technology, but maybe more importantly, where it really stands out compared to, other carbon capture methods.
Yeah, this is really where the rubber meets the road in tackling climate change. We absolutely need carbon capture that works, scales up, and, crucially, makes economic sense.
Right.
Understanding ANTECY's approach, the details of it, is pretty key to seeing how we might actually get there.
Exactly. So our mission today is to give you a clear, sort of digestible look at this cutting-edge tech. Think of it as your shortcut to getting up to speed on a potentially game-changing decarbonization solution. We're diving deep into the core science, the actual advantages, and the potential, really, of ANTECY's specific solid sorbent approach for capturing CO2 from the air around us. Okay, let's get right to it. Who is ANTECY and what's this core innovation they're bringing?
Well, ANTECY is definitely positioning itself as an innovator in this carbon capture space. Their main focus is on solid sorbents.
Okay.
Specifically, they're using potassium carbonate, that's K2CO3, you might know it as potash. Pretty common stuff, but supported on what they call apolar carbons.
Apolar carbons. Okay, that sounds like a really crucial detail. Why that specific support material? What's special about it?
Oh, it's absolutely fundamental. There's research from Wageningen University that directly compared these apolar supports, like one called SX Ultra, with polar ones, like CA1.
Right.
And the results are striking. The apolar SX Ultra captured 0.54 millimoles of CO2 per gram of sorbent,
Okay.
while the polar CA1 only 0.30 millimole.
Wow, that's almost double.
Exactly. Nearly double the uptake with the apolar support. That's a potential game changer right there, suggesting their material science gives them a big efficiency advantage, right out of the gate.
Okay, nearly twice the CO2 uptake. So what's the secret sauce? What makes these apolar supports work so much better?
The key insight, really, is that these apolar surfaces minimize the local concentration of water molecules right where that CO2 needs to react.
Ah, okay.
And this is really beneficial because it strongly encourages the carbonation reaction, basically, the CO2 binding to the sorbent. Instead of just having water molecules crowding the space, it's like clearing the stage for the main event.
That makes total sense. It's about creating the perfect little microenvironment for the CO2 capture to happen efficiently. And the report mentions they're also looking at modifying other materials, tweaking their surfaces.
Precisely. The research also showed that if you take polar supports and modify them, basically remove oxygen-containing groups from their surface, often using high heat, you can seriously boost their CO2 absorption.
Oh, interesting.
In fact, they managed to increase the uptake of that polar CA1 support from the initial 0.30 all the way up to 0.70 millimole CO2G.
Get out! So even better than the original apolar one.
Yeah, in that specific modified case, yes. It just highlights the incredible potential here for, targeted material design. It gives ANTECY multiple paths to optimize things even further.
Okay, so they've engineered this really effective sorbent material. How does it actually work day to day? How does it grab the CO2 from the air? What's the mechanism?
Well, ANTECY's sorbents capture CO2 at pretty low temperatures, below 80 degrees Celsius.
That seems low, yeah.
Which is a big plus for integrating with different industrial processes without needing, extreme heat sources.
Yeah.
And humidity plays this really interesting dual role.
Okay.
A certain amount of water vapor is actually helpful. It helps the CO2 diffuse into the inner parts of the potassium carbonate particles, which boosts the overall capture capacity.
So wait, a bit of moisture is actually good for capture? That feels counterintuitive.
It is. It's a delicate balance, though. Too much hydration before the CO2 gets to the sorbent can actually hurt performance.
Oh.
The research shows that a specific pretreatment using wet nitrogen first, then doing the actual CO2 sorption under humid air leads to much higher CO2 uptake compared to if everything was completely dry.
Interesting.
It really shows the tech can adapt to varying humidity levels in the real world, which is a big practical advantage. It's about using the humidity correctly at the right time.
Fascinating. Using humidity to their advantage instead of fighting it. Now, the report spends quite a bit of time comparing ANTECY's tech to the traditional amine-based systems. Why is that comparison so important for understanding their potential?
Well, amine scrubbing has been the workhorse,
Yeah.
right? The dominant technology in carbon capture for a while now.
Sure.
So it's the natural benchmark.
Sure.
But amine systems have some significant drawbacks. What's really interesting is the contrast in the energy needed to release the captured CO2, that regeneration step.
Right, getting the CO2 back out.
Exactly. Amine systems usually need high temperatures, which
Yeah.
means high energy use. They also tend to degrade over time, especially at those higher temperatures.
Yeah, I've heard about that.
And they can even release things like VOCs, volatile organic compounds, and nitrosamines, which raises environmental concerns.
Right, those stability and environmental issues with amines.
Yeah.
So how does ANTECY's solid sorbent approach get around those problems?
Well, ANTECY sorbents seem to offer several pretty compelling advantages. First, stability. They showed really impressive long-term stability, keeping about 80% of their initial CO2 capture capacity even after 6 months of testing.
6 months, wow. That's pretty good.
Yeah, and they also show consistent performance over repeated cycles. Capture, release, capture, release. The studies mentioned at least 10 cycles with consistent results.
Okay.
The durability and consistency could mean lower replacement costs and just more reliable operation over the long haul.
Longevity, consistency.
Yeah.
Yeah, that sounds like a big operational plus. And what about the energy side, that crucial regeneration energy?
That's another potential key advantage. Solid sorbents, generally speaking, tend to need less energy for regeneration compared to liquid amine systems. And that directly hits the operating costs.
Right.
It could make ANTECY's technology particularly attractive, where energy, especially maybe renewable energy, is cheaper. Plus, not releasing harmful byproducts. That's a clear environmental win.
Right.
This lower energy need for regeneration could really cut down operating expenses, potentially making direct air capture more economically feasible in more places.
So we're looking at something potentially more robust, greener, and maybe significantly cheaper to run. The report also points to some specific empirical findings that back up their approach.
Yeah, it reinforces that idea of needing a less watery environment right at the surface during capture to help the CO2 bind effectively.
Mm-hmm.
And we see the power of those surface modifications again. Remember the polar support, CA1, started at just 0.30 millimole.
Yeah.
By carefully removing those surface oxygen groups, they boosted its capacity way up to 0.70 millimole CO2G, actually beating the initial polar support performance.
That's incredible.
It really shows the level of precision they can achieve, tuning these materials at almost a molecular level.
That's a huge jump from just a targeted tweak. And it seems like the local climate where you put these systems can really affect the economics too.
Oh, absolutely. The report specifically calls out cold and humid climates, like in the Netherlands, as being particularly well suited for ANTECY's solid sorbents.
Right. You mentioned that earlier.
Their analysis suggests something like a 16% lower cost for capturing CO2
16%.
and a pretty substantial 33% drop in energy use in those kinds of environments compared to, say, warmer, drier places.
Wow, 33% less energy.
Yeah, that regional advantage isn't just a small detail. It could let ANTECY strategically target key markets with a really compelling cost advantage right from the start.
Okay, so for listeners maybe in those colder, wetter parts of the world, this technology might be especially interesting from an economic standpoint. Now, we've touched on the amine comparison. Let's go a bit deeper there. Amines are still the dominant players, aren't they?
They are, yeah. Mostly because they have a long track record and can achieve high capture rates. Some advanced plants get up to 90% CO2 removal.
That's high.
It is. But, like we said, they have inherent limits. Oxidative degradation is a big one. The amine molecules breaking down, reacting with oxygen and other stuff,
Right.
especially with changing temperatures and CO2 levels. Research shows that more acidic conditions and, interestingly, more flexibility in the amine molecule structure can actually speed up this degradation. That means performance drops and you get more of those unwanted byproducts.
So these systems can basically wear out over time, needing more upkeep and potentially releasing those nasties we talked about.
Exactly. And while higher humidity can sometimes help CO2 absorption initially for both amines and solid sorbents,
Okay.
for anamine systems, it drastically increases the energy needed for regeneration. You end up having to heat all that extra water just to release the CO2. It makes it very energy hungry.
Ah, I see.
That's a critical trade-off, and it's where ANTECY's technology seems to have an edge, especially in certain climates.
So the humidity that helps capture becomes a big energy penalty during release for amine panes.
Precisely. And this is where ANTECY's tech, especially that potassium carbonate on a polar supports, seems to perform really well in those colder, humid places we mentioned, like the Netherlands. They seem to hit a better balance with humidity.
Right.
And as we keep seeing, those basic material properties, that 0.54 versus 0.3 millimole uptake, give them a fundamentally strong starting point.
It really does keep coming back to that foundational material science, doesn't it? Now, let's shift to the practical side. Deploying any carbon capture tech on a large scale isn't cheap. What are the economics looking like?
Yeah, the economics are definitely complex. Retrofitting existing plants, say power plants or industrial sites, with an amine capture can work out, especially with government help like the 45Q tax credit in the U.S.
Sure.
But the upfront capital cost for these huge first-of-a-kind projects is still really substantial, very high.
Okay.
ANTECY's solid sorbent approach, though, with its potential for more scalable manufacturing and maybe a longer operational life, well, it holds the promise of lower overall life cycle costs.
Right, lower costs over the long run.
Yeah, but forming strategic partnerships with experienced engineering firms will be super important for them to optimize their supply chain and manage those initial risks.
So while government incentives might boost amine retrofits now, ANTECY's potential longevity and easier scaling could make it more cost-effective down the road. The report also mentioned the carbon capture market is set for some serious growth.
Oh, absolutely. The market projections are quite something. Experts are forecasting a really strong compound annual growth rate around 28.58%,
Wow.
leading to a market size of about USD 12.9 billion by 2030.
12.9 billion.
Yeah, this strong growth really reflects the growing global urgency and the policy support that's building for these technologies. It signals a massive global opportunity for innovative solutions like ANTECY's.
That's a huge market expansion. So how does a company like ANTECY tap into that? How do they get their tech out of the lab and into the real world?
Integration, that's the absolute key. They need to target strategically both existing industrial processes with big CO2 footprints and potentially integrate with renewable energy systems to boost their green credentials even further.
Makes sense.
Right now, the market is heavily weighted towards brownfield projects, retrofitting existing facilities,
Okay.
which makes sense, right?
Mm.
It's potentially cheaper and faster than building totally new infrastructure. Something like 83% of the market in 2024 was these brownfield projects.
Using existing infrastructure as a starting point. Smart. Are there examples of similar tech integrations that have worked that maybe ANTECY could learn from?
Yeah, there are several good examples. Shell's Quest project in Canada that successfully integrated carbon capture with an oil sands upgrader, that showed it's feasible to retrofit really complex industrial sites.
Right.
And Mitsubishi Heavy Industries has deployed their capture process in large coal-fired power plants. These show that integrating advanced capture into existing operations to cut emissions significantly is achievable.
Mm-hmm.
But the tech needs to be tailored to the specific industrial context.
So, understanding the unique needs of different industries like cement versus chemicals, it's going to be crucial for ANTECY's integration plan. And we talked about climate earlier. Does that affect where these systems are best deployed geographically?
Undeniably. As we discussed, those colder, humid regions like the Netherlands seem optimal for DAC systems like ANTECY's, leading to better costs and energy use.
Right.
So their initial market entry, their pilot projects, might be most strategic in those kinds of climates. But for drier regions, maybe strategies like pre-treating the air with water spray could help boost their sorbent performance.
Adapting the strategy based on local climate seems critical. Now, for ANTECY to really scale up, reach a bigger market, they'd need efficient manufacturing and deployment, right?
Precisely. Modular architectures are looking really promising. That's where you have standardized, mass-producible capture units that are sort of self-contained.
Okay, like building blocks.
Exactly. Companies like Carbon Capture Inc. or CC&C, with their DACC technology, they're aiming for really low costs using this kind of standardized modular design.
Makes sense.
ANTECY could benefit hugely from a similar approach. It makes manufacturing, transport, deployment easier and cheaper, especially near major CO2 sources. And, of course, strong patents protecting their intellectual property. That's essential in this competitive field.
Standardization, easy deployment key for scaling and cutting costs. And it sounds like collaborations are also going to be vital.
Oh, absolutely. Collaborative business models are proving very effective. You see different companies specializing in different parts of the CCUS value chain.
Right.
The Northern Lights project in Norway is a great example. Multiple industrial emitters share common transport and storage infrastructure.
Ah, interesting model.
Yeah, it allows companies like ANTECY to focus on what they do best, the capture tech, while partnering with others for transport and permanent storage. And government incentives, naturally, are key to making these collaborations work financially.
Sharing infrastructure, sharing expertise seems efficient, spreads the risk and cost. Now, are there specific pilot projects or case studies showing ANTECY's tech actually working in the real world?
Well, this specific report doesn't detail ANTECY's own pilots, but it does talk about the broader trend. Lots of pilot projects happening in key sectors like cement, steel, chemicals, the big emitters.
Okay.
These pilots are crucial for proving new tech works in real industrial settings. The consistent performance and stability ANTECY sorbents showed in the wagoning and research that 80% capacity after 6 months, the steady cycling detects. Those are definitely encouraging signs for success in these applications.
Right.
Plus, their technology readiness level, TRL, is at 7. That means they have a working prototype being tested in an operational environment. So they're moving towards commercial deployment.
Okay, so maybe no specific case studies yet, but the research foundation and the general industrial pilot landscape look positive. And the report also mentions using the captured CO2 utilization.
Yes, and that's becoming a really important piece of the puzzle. The report mentions innovators like Mission Zero Technologies, turning captured CO2 into products like limestone.
Oh, cool.
And Deep Sky Alpha in Canada, building a multi-technology hub aiming to remove large amounts of CO2 annually. These show the potential for ANTECY not just to capture CO2, but maybe to plug into these growing carbon utilization pathways, turning a waste gas into something valuable.
That's circular economy thinking, not just capture and store, but capture and use. But scaling up any of these techs faces big challenges, right? The report acknowledges that.
Absolutely. High upfront capital costs are still a major hurdle, especially for newer technologies like ANTECYs. And navigating the complex, often changing regulations and permitting processes, that can be a big challenge too.
I can imagine.
This is where things like public-private partnerships, like the one mentioned for Mission Zero, can be really critical, sharing the financial load, streamlining the path to market. And again, strong patents are vital for attracting investors and partners.
So it's a mix. Keep innovating the tech, build strategic partnerships, push for supportive policies, and have a plan for CO2 utilization. Now, let's look at the competition. Who else is doing interesting things, and how does ANTECY stand out?
Yeah, the DAC landscape is really dynamic, definitely evolving fast, all driven by these net zero targets. You've got companies like Spiritus working on a passive fruit sorbent aiming for ultra-low energy and cost.
Interesting.
And Carbon Collect, with their mechanical tree design, focusing on very efficient passive capture using wind.
Okay.
ANTECY's differentiator is really that specific material choice, potassium carbonate on polar carbons. It seems to offer a good balance of CO2 uptake and long-term stability, especially compared to older amine systems, particularly when temperatures fluctuate. Their patent, that WO 2019 number, gives clues about their focus on material design.
So that material combination is their niche, their competitive edge in performance and stability. What about other emerging DFAC approaches?
Well, there's Avnos. They have a hybrid system that captures both CO2 and water, focusing heavily on low energy use.
Captures water, too.
Yeah, so while Avnos emphasizes energy efficiency through that dual capture, ANTECY's tech, with its boost from humidity, has different advantages, particularly in certain climates. And the strategic approach varies too. Some companies try to do the whole chain capture, transport, storage, others specialize. For ANTECY, focusing on capture and then partnering for transport and storage like the Northern Lights model, or maybe working with transport companies like EnLink that might be a smarter, less capital-heavy path to scale up.
Makes sense.
Exploring collaborations with places like Haflin Oslo Celsius or ARC's Amager Bake Plant, facilities looking to add carbon capture, could also be good opportunities.
Specializing and partnering seems prudent in such a complex, expensive field. And the report had insights on global patent trends, too.
Yeah, the data from 2000 to 2021 showed a lot of innovation activity in CCUS, with Europe and North America really leading in patent filings.
Okay.
Which just underscores how important it is for ANTECY to have a solid IP strategy, knowing where and when to file patents to protect their innovations in key markets.
So understand the competition, know your unique strengths, partner strategically, protect your IP, all crucial for success. Now, zooming out globally, what are the big market forces and policies shaping the future of carbon capture?
The global CCUS market is really on an exponential growth curve. Projections show a compound annual growth rate near 40%, hitting maybe over $60 billion by 2031.
Wow, nearly 40% growth.
Yeah, huge growth. And it's being heavily driven by government policies and incentives. In the U.S., you've got the Inflation Reduction Act, the enhanced 45Q tax credits, making projects much more financially viable, paying per ton of CO2 captured and stored.
Right.
Europe has its innovation fund, pumping money into large-scale clean energy tech, including carbon capture.
Those government incentives seem absolutely pivotal then.
Totally.
Yeah.
And you can often link regional innovation spikes like surges in patent filings directly to big policy announcements like the European Green Deal or the U.S. infrastructure law.
Interesting correlation.
It strongly suggests ANTECY needs to watch global policy closely. and identify regions with strong R&D and supportive rules for partnerships and maybe initial market entry.
So keeping tabs on policy is just as vital as the tech development. Are there big established players ANTECY could learn from or even work with?
Definitely. Look at ExxonMobil. They're a major player in CCS, have lots of pipeline infrastructure, and ambitious capture targets, aiming for 30 million tons a year.
Okay.
Their partnerships with big emitters like CF Industries and tech providers like Lind show how collaboration across the industrial ecosystem can work. ANTECY could potentially learn from that, maybe forming alliances with other big CO2 emitters.
Makes sense.
And policy advocacy is key too. We need streamlined permitting, clear rules on CO2 storage ownership, more transport networks.
Mhm.
ExxonMobil is heavily engaged in that advocacy.
Right.
That's a model for ANTECY, advocating for policies that support their day's tech, leveraging things like the IRA credits to get capture costs down, aiming for that crucial sub $100 per ton target.
So learn from leaders, advocate for good policy, build partnerships. Finally, looking at the really big picture, what's the scale of the global need here? Why is ANTECY's work so important?
The scale is just immense. The climate challenge is huge. Leading climate science groups project we need to capture and store or use over 6 billion tons of CO2 per year by mid-century.
Billion with a B.
Billion, yeah, around 2050. That's what we need for a realistic shot at meeting global climate goals.
Wow.
The massive gap between where we are now and where we need to be. That represents a truly significant opportunity for innovative, scalable solutions like ANTECY's.
A significant opportunity driven by a profoundly urgent global need. Well, that brings us towards the end of our deep dive into ANTECY's solid sorbent technology. Let's just quickly recap the key takeaways.
Sure. ANTECY's approach, using that potassium carbonate on a polar carbons, looks really promising. It seems energy efficient, environmentally sound for direct air capture. It offers compelling advantages over traditional amines, especially on stability, lower regeneration energy, and fewer harmful byproducts.
And those core innovations, the specific materials, the performance boost in humid conditions, the potential for modular scaling, they really position ANTECY as a company to watch in this critical field.
Indeed. This technology really holds significant potential. It could be a key contributor to global decarbonization, especially if it's deployed strategically in the right climates and supported by the right policies.
So here's a final thought for you, the listener, to mull over. As we all grapple with the increasing urgency of large-scale carbon removal, how might technologies like ANTECY's fundamentally reshape our industries and help pave the way to a sustainable future? And what other groundbreaking innovations might be just around the corner to boost their impact and speed up our transition to net zero? A vital question to keep thinking about. Thanks for joining us for this deep dive.